The cryosphere is a key component of the climate system. I'm Damien Mansell, and this week I'll be exploring a major part of the cryosphere, ice sheets, and how they will respond to climate change. As our planet warms, sea levels are set to rise. The current contribution to sea level rise is mostly from thermal expansion of the oceans and melt from mountain glaciers and small ice caps. But what about Antarctica and Greenland? Together, these ice sheets make up 99% of the glacier ice on Earth. That's equivalent to about 65 metres of sea level rise. 65 metres of sea level potential isn't a forecast or prediction, it's just to say how much ice is locked up in these ice sheets. Now 65 metres of sea level potential is a lot. Exeter Cathedral is around about 44 metres high. Prior to the early 2000s, it was thought that in a warming climate, both melting around the margins and precipitation in the interior would increase, causing the ice sheets to grow in the middle and shrink at the edges. It was thought that an increase in snowfall will offset the melt at the margins and there will be no change in how the ice flows, the ice dynamics. But the reality is that Greenland has shown a very rapid response to warming over the past 2 decades. Ice loss has increased over this time, with glaciers showing an increase in flow speed, a frontal retreat and thinning of the ice. For Greenland, half of the total mass loss is from surface melt, whilst the remainder is due to blocks of ice breaking off, forming icebergs where the glacier meets the sea. This process is known as calving. So how do ice sheets move? Well, like all things, they tend to spread out under their own weight. Soft things, like treacle, will spread out easily, whereas strong things will resist spreading. Ice sheets are piles of compressed snow that forms glacier ice. If it snows more, the pile will get larger and you have a positive mass balance. If you increase the melt rate and it's larger than the amount of snowfall, then you'll have a negative mass balance and the pile will get smaller. If the pile spreads faster, then more ice will get to the edges and so the melting will increase when you have a larger amount of ice lost as iceberg calving. So let's look at these mass loss mechanisms in turn. On average in the summer, about half of the surface of Greenland's ice sheet naturally melts. At high elevations, most of that meltwater quickly refreezes in place. Near the coast, some of the meltwater is retained by the ice sheet, and the rest is lost to the ocean. In 2012, nearly the entire summer experienced above normal melt extent across the Greenland ice sheet. Much of this can be attributed to a shift in the regional scale patterns of high and low air pressure systems in the North Atlantic. Nonetheless, the melt extent was the largest in the satellite era, extending up to 97% of the ice sheet surface and lasting 2 months longer than the 1979 to 2011 mean. Greenland may be near a tipping point. If the average annual temperature on Greenland increases by around 3 degrees Celsius, then the ice sheet might melt at a rate which will tip it into a new, smaller inland form. But melt is only part of the story. Much of the increased mass loss from Greenland has resulted in an increase in ice flow or spreading. So more ice is flowing to the margins and is being lost as icebergs. Basel lubrication occurs in Greenland when meltwater drains to the bed. Surface meltwater that hasn't drained to the bed or margins can collect in topographic depressions on the surface to form lakes. These lakes can be up to 9 square kilometres in area and form all around the edges of Greenland. Since the lakes are darker than the surrounding ice, they absorb more sunlight and so have a warming effect on the underlying ice. These lakes can drain abruptly, sending a substantial amount of meltwater through the ice sheet to the bed. When the meltwater reaches the bed, it can have a lubricating effect on the ice sheet flow, causing short-lived acceleration events. In addition, the meltwater transports heat to the interior of the ice sheet, which is warmer than the surrounding ice. This may have a warming effect on the ice sheet, softening it and allowing it to deform and flow faster. Another controlling process on ice flow is buttressing, which can oppose spreading. Just like the buttress on a cathedral holds the walls up, buttress around an ice sheet can resist ice flow. An ice sheet spreads under its own weight to the coast, where it either runs aground on a high spot in the bed, is topographically constrained, or flows over the ocean, forming a floating ice shelf. If you lose the floating ice shelf, or retreat off a high spot in the bed, you remove this friction component, which is effectively your flying buttress. The resistive stress is removed, which causes the feeding glaciers to flow faster and mass loss increases. This is what happened on the west coast of Greenland at Jakobshavn Isbrae, one of the fastest flowing glaciers in the world. On the left of the animation is floating ice made up of icebergs and sea ice. On the right is the ice cliff where the terminus of the glacier meets the ocean. In 2001, the ice was out here, and Jakobshavn Isbrae had a large ice shelf or floating ice tongue, the flying buttress. In the following years, the ice thinned and the floating ice shelf broke up all the way to the ice front margin. Since measurements of Jakobshavn Isbrae were first taken in 1850, the glacier has gradually retreated. However, the retreat shown here from 2000 to 2006 was at this time accompanied by an almost doubling of glacier flow speed. It is important to note that the loss of the floating ice did not contribute to sea level rise, but the acceleration of the glacier ice did. Jakobshavn lost its floating tongue, its flying buttress, and so more land ice flowed to the margins and carved off as icebergs into the ocean, which has a direct contribution to sea level rise. When reporting on calving events, it is really important to remember that it is a natural ablation mechanism along with melting, and may balance with accumulation over the Greenland ice sheet. In the case of Jakobshavn Isbrae, there was rapid retreat and thinning, which was accompanied by a speed up of the ice tongue. This led to unprecedented mass loss. Recent studies show that much of the mass loss from Antarctica and Greenland has resulted from an increase in ice flow to the oceans. This discovery means today that our best estimates are limited, and so we need to continue to monitor the ice sheets to reduce this uncertainty. Are these accelerations going to be sustained in the future, or even increase? As well as anthropogenic warming, ice sheets are affected by many natural processes, such as multi-year fluctuations in the atmosphere, for example, shifting pressure systems in the North Atlantic, or slow changes in the ocean currents. To reduce uncertainty about future sea level rise, we need to continue to monitor the ice sheets to better understand the controlling processes which affect ice sheet flow.